Okay, we're going to have a couple announcements and reminders before we start. So the first is that the Exam 3 review is going to be at the end of this week. So same schedule as normal, Friday at 2 p.m. That's the 22nd, I believe. 2 p.m. And the room for that is always going to be SEC 102, and yes, it will be recorded and put on YouTube afterwards. So that's coming up this week, and then for the rest of the semester, my office hours are going to be posted on Blackboard, so they're up there now. Could change a little bit, but probably not. So they are a bit expanded, because I expect we'll have a lot of people wanting to ask questions about the last two exams, and when the time comes about final grades and things like that. So check that for my full availability. If you need to meet with me outside of that time, just please send an email and we'll try to work something out. And then we'll get to this a little bit later because it's not immediately on your mind, but then we'll have, next week will be the final exam review, which we will do in 3 parts. So Tuesday, Thursday in class, and then Friday we'll have another session, same time as this week's session. I will probably just do it based on each third of the course. So exam 1 material on Tuesday, exam 2 material on Thursday, and then the newest stuff on Friday. There'll be 34 total questions, just like the real final exam, but that's too much to cover in one day. So we'll break it up into 3 days. Should be plenty of time to get all that done, since we are gonna finish the course material this week, if all goes as planned. So what I'll start with today is I think this will be our last Try Hard Tuesday. You guys are probably happy about that because you probably don't like when I talk these things. But anyway, because I don't want to interrupt the exam reviews with this. Maybe I'll do one next week, depends on how I'm feeling. But anyway, I've had a lot of questions about this, and I've talked to some individual students about it, but I think it's good to bring these things up to the whole class. What final grade can I get? So we've had 2 exams, we still have 2 more left, so a lot of the course is still there. So we have, the third midterm and the final count for 54% of your grade, and those are still coming up. So your grade can change a lot. But then the question is, how likely is it to change? And so I went through data from spring 2019, which was, again, the last time I taught this course that wasn't affected by COVID, so it's the most accurate representation for what we can expect this semester. That was about 450 students who finished the course without dropping. So that's a pretty good sample size, so I don't expect the trends are much different from year to year than that. And basically, on average, a student's final grade was 2% lower than their grade after the second exam. That's approximate because I didn't calculate their exact grades at that point, but it's about that amount. So there's a little bit of a drop off, but again, on average, most people's grades stay about the same as they are now. So I calculated your grades at the midpoint, or after exam 2, I guess. So you guys already know what those are. And so on average, that's where you're going to likely be. But of course, there's a wide range of possibilities within that average. It's a huge spread of values. But around 75% of the students, again, their grade didn't increase or decrease more than like 9%. Now 9% on our scale is usually a whole letter grade. So that'd be like going from, a C to a B, or in the opposite direction, a C to a D. So that's, a pretty significant change, but still, for the majority of students, you're going to be within 1 letter grade of where you are now. That's how it typically works out. Now, the caveat that I give to everyone that I talk to this about is, statistics on past outcomes don't predict the future for an individual person. So you can look at this as sort of a guideline of what are, the most expected outcomes, but of course your specific outcome depends on what you do with the next few weeks in this course. So, keep in mind that there's a whole range of possibilities. This is just sort of reporting what's average or what's typical, but not all cases. And then there's a question of how do you calculate the maximum grade you can get? Of course, this is, in most cases, fantasy land, right? Because calculating your maximum grade requires you to get perfect scores on the third exam and the final, which probably less than 1% of students will do. And so that's not a likely outcome, but it gives you an idea of, again, what range of possibilities are available for you. So when we calculate your final grades, remember that the numerical exam scores, 20 points each for the midterms and 34 for the final, those are not going to be weighted. They count towards 94% of your grade, and each one then counts exactly as it is numerically, so you don't have to weight that or calculate a percentage for that. So if you want to figure out your maximum grade, you just, for what we have so far, which is 2 exam scores, you sum those up, you add your scaled homework score. So in an email I sent about a week or so ago, I told you how to calculate your homework score out of 6. That can change a little bit because we always drop your 2 lowest and we have a few more assignments to go. But roughly that's going to be about the same as it is at the end of the semester, and same with your bonus points, which are currently also calculated for you. So you'll have those 3 numbers, you'll add them together, and then for the remaining exams, if we're talking about from today, when you still have the third midterm and the final, there's still 54 more points to go. So you basically take the points that you've earned, which are calculated here, those are the points that you've earned so far, and you add 54, and that will give you the maximum number of points you can finish the semester with. Again, assuming your homework score and bonus score don't change, which is a relatively safe assumption at this point. So those are your earned points, then you add to those the possible points, or if you want to do this after the third midterm exam, then you just have the 34 from the final to add on is what your maximum will be. And then you can also play the game of, well, what grade do I need on the final to get this grade in the course? So you look at the numerical grade you want, you subtract it from the points that you've earned, and that tells you how many more points you need on the last two exams. So that math is very, straightforward as well. But if anybody wants to go over that with me individually, I'm happy to talk to you about it. And again, it gives you sort of an idea of what your possibilities are, but of course your individual outcome will depend on a lot of things. So don't be shy about asking questions about your standing in the course. And I've had a lot of those conversations already. The drop deadline is tomorrow, so if you're considering dropping the class, it's good to have a clear picture of where you are at this point in time. All right, any questions on that? Okay, so what we'll go into then is the course material. So we're going to finish with 3 example problems that we had planned for last time. So these 3 things will be relevant to stuff that's on the third midterm. Phase diagrams is the last topic that will be covered on that exam. Then we'll go into new stuff later that's only going to be on the final. So we did a bunch of these last time. We're going to finish with the last few here. So in this problem here, we're talking about taking a substance and changing the conditions in some way. So we're starting at 0.2 atmospheres and 100 Kelvin, and then we're increasing the pressure to 2 atmospheres while maintaining a constant temperature. So we want to know which of the following in the correct order lists the phases that will be encountered during this process. So what we're doing is we're starting at 0.2 atmospheres and 100 Kelvin. So atmospheres, the pressure is going to be on the y-axis, temperature on the x-axis. So we're starting right there. That's our starting point. And then we're raising the pressure to 2 atmospheres, keeping the temperature constant. So we're going to keep the temperature at 100 Kelvin, and we're going to go all the way up to here at 2 atmospheres of pressure. So that's going to be our end point in this process. So then what we want to figure out is which phases do we encounter as we go from here to here. So we're just going to traverse through the phase diagram. So we're starting down here in the bottom right. So remember that when we label a phase diagram, bottom right is gas, top left is solid, middle is liquid. So those are the 3 regions. So at the starting point, we have gas phase. So the only answer that has that is the first one is D. So if we trust ourselves, we could just pick D and be done. But let's make sure the rest of choice D works out as well. So we start there. As we raise the pressure, we get to this line here. And as we cross that line at 0.4 atmospheres, we're going from gas to solid. So when we raise the pressure at that temperature, we're going to go straight from gas to solid. We're going to do basically a reverse sublimation, whatever that's called. And then we're going to keep raising the pressure, and we're going to cross another phase change line. So here at about 1.6 atmospheres, we're going from solid into the liquid. So we're encountering all 3 phases in that order, and then we end up in the liquid part of the diagram. All right, so we're going to go gas, solid, liquids. That would be choice D, gas, solid, liquid. That's the order that we'll encounter those 3 phases as we go. So you wouldn't always encounter all 3 phases, but at this particular temperature with this increase in pressure, we will go through all 3 phases in that order. All right, any questions, let me know. All right, the next one here asks about the relative densities of the solid and liquid phases. So what you'll recall is that the slope of the solid-liquid line, so here we're considering solid and liquid, so those are those 2 parts of the diagram. And this is the line that divides those 2. And the slope of that line tells you the relative densities of those 2 phases. So if you start here in the solid part of the diagram, when you raise the pressure, that's equivalent to making the substance more compact. As you increase the pressure, you're packing everything closer together, so you're making it more dense. So when we raise the pressure, as we saw in the last problem, as we go up and up in pressure at a constant temperature, eventually we cross over from solid to liquid. So what that means is that as we're making the substance more dense by compressing it, it's going from solid to liquid. That means the liquid is more dense than the solid. So whenever you have a negative slope for your solid-liquid line, that tells you that the liquid is more dense than the solid. All right. If this line was perfectly vertical, that means they have the same density, though you won't normally see that. But here we have a slight negative slope to our solid liquid line, which means as we compact the material, it's going to go from solid to liquid. And this would be the situation you would see for something like water, which is another substance where that's going to be true. All right, any questions on that? Okay, and then the last one we'll have is this one here. What is the vapor pressure at 250 Kelvin? So vapor pressure is one of the things that we can easily read off a phase diagram. We had equations for that as well. But what we're going to do in this is, again, for vapor pressure, we go to that specific temperature, 250, and we find out where that intersects the gas-liquid line. So this is liquid here, and this is gas, and one of the significances of this gas-liquid line is that it tells you the vapor pressure of the liquid at any given temperature and pressure, wherever that line occurs. So when we get to that line here, we're at this pressure. Again, that's the pressure at which the substance the vapor pressure would equal the atmospheric pressure, and that's where you would see boiling occurring, and that's about a little bit over 1.2 atmospheres. It's probably a little bit higher, but anyway. In an approximate sense, it's going to be about 1.25 atmospheres, somewhere around 1.2. All right, so again, we read up from that temperature, find the liquid gas line. That's going to tell us the vapor pressure at that temperature, which is, again, right around 1.2. Okay? So any questions on that? So, yes, in the back. The critical point would be point E here. So that's where the gas liquid line just seemingly ends. So that's your critical point. And again, the significance of that is when you get to the critical point anywhere beyond this, so anywhere up in this top right quadrant up here, you don't have separate liquid and gas phases anymore. You just have one phase that's called a supercritical fluid, which on some level behaves like a liquid and a gas, but there's no longer a phase change that can occur after that point. So the critical point is where that ends. The triple point would be here where the three intersect. So that's another thing that we talked about a little bit last time. The triple point is where all three phases can exist at those conditions. Okay, any other questions? Okay, so what we're going to move into now is the new stuff. So this is going to be the end of exam 3 material, just to make sure that we're clear on that. So the stuff we're going to cover now for the rest of today and on Thursday will only be on the final exam and only on the last homework assignment as well. And we're going to talk about the third phase of matter that we have not talked about a lot yet, which is solids. So we did talk about some phase changes involving solids, but we haven't really talked in detail about the properties of solids, the structures of solids, and that's what we're going to get into starting today. So the first thing we have to do is classify different types of solids. Now in terms of their structure, there's two major classifications, amorphous and crystalline. That's what we're going to start with first. What we will also go through in this part of the course are some different chemical classifications of solids, different types, metals, ionic compounds, what are called network solids, molecular solids. So there's also some chemical classifications within solids as well. But from a structural standpoint, there's two basic types, amorphous and crystalline. So amorphous solids are solids that have no regular structure. So whatever the building block is that makes up an amorphous solid, whether it's a molecule or whether it's an ionic compound that's made up of cations and anions, they don't have a regular arrangement. They're kind of just randomly piled together. All right, so in other words, the atoms and molecules, whatever makes this up, are just arranged randomly. And we're actually not going to say too much about amorphous solids because there's not much you can really say about their structure. Again, everything is kind of just randomly piled together. There's no regular order to the structure, so not really a easy way to classify them. What you should be aware of for amorphous solids, and probably the only thing we would likely ask you about them, is what is an example of amorphous solid? The classic example that you've encountered in your everyday life is glass. So some people say that you may have heard before that glass is actually a liquid. That's not really true. Glass is an amorphous solid, so it's still a solid. It doesn't change its shape or it doesn't occupy all the available volume like a fluid would. But in the same sense as a liquid, it doesn't have like a regular arrangement of the atoms in the structure. It's just kind of all sort of random and all over the place. So glass is the classic example of an amorphous solid. Now the type that we're going to talk about the most in here are called crystalline solids. So these are solids where the components are arranged in highly irregular and periodic fashion. So you'll have simple building blocks that make up these solids, and they're going to repeat themselves over and over again in all dimensions. All right, and there are many examples of crystalline solids, which you've again probably seen in your everyday life. We've talked about diamond a little bit. Diamond has those nice facets and edges that give it its beautiful appearance, and that's because of the regular arrangement of carbon atoms that are in that structure. And then a lot of ionic compounds are crystalline, so sodium chloride salt, you notice when you shake it out, it looks like little, cubic crystals, and that's going to be something we'll talk about at the end of this. And then sugar can be crystalline as well, usually in the form that you buy. So there's a lot of examples of crystalline solids, and in that case, the atoms or molecules that make them up are arranged in regular periodic fashion. They're arranged in all directions, and it's a repeating pattern that you'll see if you look at that at the microscopic level. So to classify crystalline solids and talk about their structures in more detail, we have two key definitions, lattice and unit cell. So these are not types of solids, but these are definitions that are associated with crystalline solids. So a lattice is a three-dimensional system of points Now, lattices don't have to be three-dimensional in a more general sense, but the types that we'll talk about in this course are all three-dimensional lattices, and each point in the lattice represents an atom or a molecule, depending on the fundamental building block of that structure, but it's going to represent one of those building blocks in the crystal. Now, there's a lot of examples of lattices more in an everyday sense too. Again, some two-dimensional, some three-dimensional. So if you look at the beautiful carpeted floor in this room, probably like 1985 vintage or whatever, you can see there's a regular pattern of squares in different colors that go around the whole room. So that's an example of a lattice. It's a repeating pattern of points or whatever little building block you have. So if you imagine each of these squares is a different atom or ion in the crystal, then the lattice would be the whole thing sort of arranged in a regular repeating fashion. That's what we call a lattice. And then what sort of makes up that lattice and the piece that we need to really focus our attention on is called the unit cell. So the unit cell is the smallest repeating unit in a crystal. But it's more specific than that. It's not just the smallest repeating unit, but it's the smallest repeating unit where you can generate the lattice by just taking that unit and stacking it in all directions. So the lattice is generated by translating the unit cell in all directions, basically by stacking it in all directions. All right, so the type of, and I guess I should say all three directions, so we're talking about three-dimensional lattices in this course. So the type of unit cell we're going to focus 99% of our attention on are cubic unit cells. So these are going to be little cubes that are going to have atoms or molecules arranged on the different parts of the cube, corners, edge, and sides. And so each of those cubes is a unit cell, and the lattice is generated by stacking those cubes in all directions. So think of it just like stacking building blocks. Imagine you have a cubic building block, and you're just arranging a huge stack of that. That would be your lattice. And each of those little building blocks, each of those little cubes is called the unit cell. So that's how we generate these crystalline structures. Again, they're repeating structures, they have regular order to them, and so you take these little unit cells that are usually cubic in shape for the type that we'll talk about, and you just arrange them in all three directions, stacking them on top of each other like blocks. Okay, so those are some definitions that we'll talk about. And then within crystalline solids, there are a few different types. Two of these we will talk about in detail. So the first one is called an atomic solid. It can be a nonmetal or a metal. The example that I'm showing here is diamond, a small piece of the diamond structure with carbon atoms at each point. But the key thing about an atomic solid is that it's made up of one type of atom. So it's always going to be an elemental substance. So examples of atomic solids, again, the one that I'm showing here is a small piece of the diamond structure, which is made up of carbon atoms, a nonmetal. But then most metals also would be classified as atomic solids. So we talked about the standard states of elements. Every metal except for mercury is a solid, and most of those solids exist in a crystalline form that would be classified as an atomic solid, which is one type of metal atom repeating itself in all different directions. And then the other type that we're going to talk about in this course, not until the end next time, are ionic solids. So again, most ionic compounds exist as crystalline, in their crystalline forms, where you have positive and negative ions that make up the lattice points. And they're going to, again, repeat themselves in all directions. So we're going to talk about a few different types of ionic structures in this course, including sodium chloride, zinc sulfide, which is another structure type, and then you have 2-to-1 compounds, etc. So pretty much any ionic compound can exist as a crystalline ionic solid. And then the last type, which we'll talk a little bit about the properties of, but not so much their structures, are called molecular solids. So these are going to be covalent compounds where the fundamental building block is a molecule. And so the lattice points in these molecular solids are going to be molecules. And what's going to hold those molecules together are going to be intermolecular forces. So we talked about intermolecular forces at the beginning of this chapter. And so the molecules in these are held together by intermolecular forces. So they are discrete molecules, but they're held in place into a regular crystalline form by virtue of these intermolecular forces. And the example that I'm showing here, and a classic example of a molecular solid, is ice. Other common ones would be any of the diatomic elements in their solid form. So the one that naturally occurs as a solid is iodine, I2. We said that's a solid at room temperature. And so that would be I2 molecules held together by just London dispersion forces. In ice, you have a lot of hydrogen bonding, so that's a stronger force holding it together. But nonetheless, they're going to be, anytime you take a molecular compound and convert it into a solid crystalline phase, it would be classified as a molecular solid. So those are the three major types. The first two are the ones we're going to talk about the structures of in more detail, starting today with metals. Now, to talk a little bit more about metals, one of the first things we're going to talk about is going to be the metallic bonding. How are the atoms and the metals sort of bonded together to each other? So we haven't talked about metallic bonding yet. We've talked about covalent bonding, which is two atoms sharing electrons. We talked about ionic bonding, where the electrons are completely transferred and you have a positive and negative ion sort of held together by static electricity type forces, electrostatic forces. But the metallic bonding is the third major type of bonding that you can have in substances. And as the name suggests, it occurs in pure metals. So what happens in metallic bonding is that if you recall one of the key properties of metals we talked about all these periodic trends, radius, ionization energy, all that stuff from a long time ago. So metals tend to have low ionization energy, right? They're on the left side of the periodic table. That's where the ionization energies are low. And so what that means is that the outer electrons in metals aren't held very tightly. They're not really stuck to the nucleus really strong. So when you arrange metals into a solid, into a regular crystalline structure like we're going to talk about, what happens is that those valence electrons are not going to be localized on a single atom, or they're not going to be shared between just two neighboring atoms. They're going to be delocalized over the entire structure. So you have these mobile electrons in the metal. So all the valence electrons in a metal are going to be just moving around freely around the whole surface and around the whole structure of the metal. Question in the back? So delocalized means that they're all over the place. They're not stuck in one place. They're not belonging to one atom or not shared by two atoms. They're just moving all over the crystal. They're completely unbound, basically. They're bound by the nucleus. They're not going to just fly off into space, but within the structure, they're able to move freely. So that's what we mean by delocalized. So if you have a group 1A metal, like sodium, what you can think about in terms of the bonding in this structure, how are the atoms sort of held together, bonded to each other, is you have one valence electron. So you'll have these what are formally positive cations, where their outer electron is able to be lost pretty easily because of the low ionization energy. And then you'll have, let's see how well it shows up here. You'll have these delocalized electrons, and I'm going to just indicate with, I don't know if I can do that bigger or not, no. Oh gosh, that's not what I wanted to do. Okay, this current version of the software is not good at drawing highlights. But anyway, what I'm drawing in yellow highlights here are basically delocalized electrons, which we call a sea of electrons. Basically just the valence electrons that are able to move around freely around the whole crystal. They're not bound in place in any sense. So what I'm showing in yellow here in these cartoons are what are called the sea of electrons, the valence electrons that are able to move freely around the structure, and that's what is defined as metallic bonding. And so then if we have a group 2A metal, in that case you have two loosely held valence electrons. In group 2A, which is the second column, you have two valence electrons, and so both of those valence electrons can move around and be delocalized over the whole structure. So you can almost think about this as a bunch of 2+ cations now, sort of held in place with these freely moving electrons kind of swirling around them. And so again, you'll have this sea of electrons. This time it'll be two valence electrons per metal that are delocalized, but again, all just sort of moving around the whole structure, not clearly localized. So you can't clearly define where the electrons are, they're moving everywhere. Okay? And so in any type of metallic structure, all valence electrons are loosely held and delocalized. That's the key aspect of metallic bonding. All right, so that's going to be how it works for metallic bonding. That's what sort of holds the atoms in place. And again, it's not localized bonds. It's going to be delocalized electrons floating around the whole structure. So then let's talk about some of the properties of metals, which are all related to this sea of electrons. So if we talk about the relative melting points of metals, we said that most metals exist as solids at normal room temperature conditions. Most of the metals, except for mercury on the periodic table, are all solids. And so they would have moderate to high melting points. All right, so some metals melt pretty easily, others not so much. But it's because you have, again, those loosely held electrons. So those electrons are sort of holding the atoms together. So if you want to melt the substance, you do have to disrupt that local that regular structure and some of those attractions between the metals. But nonetheless, you can melt them pretty easily because even in the liquid form, that metallic bonding can still take place because the atoms are still in contact with each other in the liquid form. The electrons can still be delocalized. So even mercury, which normally exists as a liquid, that still has metallic bonding. That still has the sea of electrons, those mobile electrons that can move around. It still has a lot of the other properties that are associated with metals. But in the liquid form, things are not as ordered, so the atoms are moving around more freely, but you still preserve that. So it takes some energy to break apart that regular structure, but it's not too much. So again, the melting points for these are, in most cases, moderate to maybe a little bit high in some cases. But we can make trends as we go through the metals. So if you go across a period, which is left to right on the periodic table, so especially in the main group metals, let's go to the periodic table just to reorient ourselves on that. So we can talk about periodic trends with melting point now that again relate to the metallic bonding in these in these elements. So if we go across a period, in particular it's straightforward if we compare group 1 to group 2. As we said about in the last slide, in group 1 you have one valence electron per metal that's going to be delocalized. In group 2, you have two valence electrons per metal that are going to be delocalized. So you have more forces of attraction in the group 2 metals than in group 1 because you have twice as many valence electrons holding everything together. So because everything is held together more strongly with more valence electrons, that makes it harder to melt those elements. They're held together by stronger forces, so you have to put more heat in to break those apart. So as you go across a period, in particular if we just compare group 1 and group 2, where that's a very straightforward situation, you're going to increase the melting point as you go from left to right. And again, that's because you have more valence electrons, so you have a higher charge in the structure, more delocalized electrons, higher charge on the nuclei that are left behind, and that leads to stronger attractions between the metal ions in those structures. All right, so in general, as we talked about in other contexts, the more attractions you have between protons and electrons, the more electrons or more protons you have interacting with each other, the stronger things are held together, and that's true in these metallic structures as well. Now, as you go down a group, as you go from top to bottom, so within a column of metals, like let's say from lithium down to cesium or beryllium down to barium, again, mainly focusing on main group metals for these arguments, but as you go down from top to bottom, we can think about what happens there, and in that case, the melting point is going to decrease. And that's because in this case, you have larger atomic radii. So the core electrons that we can again represent as positive cations where the delocalized electrons are swimming around. If you have larger metal ions, that means you have a weaker attraction to the electron C. So in other words, the delocalized electrons in those structures are further away from the nuclei that they're attracted to, and that results in a weaker attraction between them, easier to break them apart. Okay, so the melting point will decrease as we go from the top, like lithium on top of group 1A, down to cesium, which is the bottom of that same group. So that's because the electrons are further away from the nuclei, held together less strongly as a result. If you want to talk about the boiling point of metals, which is not something we typically deal with, metals have very high boiling points though. All right, we said that you can maintain the metallic bonding to some extent when you melt it, because the atoms are still in contact with each other and the electrons can still swim around. But when you boil something, you have to separate the atoms completely, which requires you to break all of those metallic bonds between the atoms. And so it's difficult for what are the cations in the structure, the core structure, which is cationic, and the valence electrons that are swimming around in that sea of electrons. It's difficult for those to be completely broken from each other. All right, so in general, you have to put a lot of energy into something to boiling it because you have to break all of the forces of attraction. But in metals, it's particularly high because the forces of attraction that are holding those metal ions together are, again, those electrostatic interactions between the delocalized electrons and the nuclei. And in order to boil it, you have to break all of those apart, so that's a lot of energy. All right, so metals tend to have moderate to high melting points, which we can predict based on their location in the periodic table. Boiling points are very high for these substances. Now, the other two properties of metals that we're going to talk about are their mechanical properties and their electrical and thermal conductivity. Again, just at a very basic level. We're not going to go into a lot of detail with these. Mechanical properties basically means, how does the material behave under stress, when you try to distort it, when you hit it with a hammer, when basically what is it sort of, how hard is it, how soft is it, stuff like that. That's what we mean by mechanical properties. So the key mechanical property of a metal is that they are what we call malleable. And really they're the only major class of substance that would have this property. Malleable is another way to say bendable, so we can bend metals. All right, so if you've ever done one of those feats of strength competitions, you can bend a metal bar if you're strong enough, and it doesn't break, it doesn't snap in two, it will bend to a pretty good extent. And the reason for this is, again, because of the delocalized sea of electron type bonding that we have. The metal ions, they're not tightly held in place because the electrons are delocalized, so they have a little bit of room to sort of move around. They can still maintain contact with those delocalized electrons even if they're shifting around a little bit. And so as a result, they can sort of bend around, they can sort of distort, and that's not going to completely disrupt the bonding when you do that. So it's very possible to bend these structures. And so the metal ions that are in these structures can in some sense slide through the sea of electrons, all right, because they're not held in place by localized bonds. But again, this is delocalized sea of electrons. And so they can slide in place. Slide through that's the word slide, with quotes on it.
Oh, I meant the word slide, like...
Can?
Yeah. Oh.
Sorry. All right, so the metal ions are not held too tightly in place, and they can kind of slide through that electron sea, because they'll still maintain contact with the electrons even if they're moving around within that sea of delocalized electrons. That allows, on a macroscopic level, for the metal to bend, because the atoms can move around and not totally disrupt the bonding that's in place in that structure. And then, as we probably already know, especially if you've taken the physics courses here, metals have good electrical and thermal conductivity. So that means they can conduct electricity as well as heat very well. And that's going to be true both in the solid or the liquid state. Whenever you have that metallic bonding in place. So for example, mercury, which we know is a liquid metal at room temperature, that is also a good conductor even though it's a liquid. So this is not specific to solid metals. And that's because the electrons in these structures are mobile. And it's particularly obvious how that relates to electrical conductivity. Because when you want to conduct electricity from one point to another, you need electrons to move through from one point to the other. And so because the electrons, the valence electrons in metals are highly delocalized and mobile, it's easy for electrons to move through the metallic structure, and that gives rise to electrical conductivity. Thermal conductivity is a little bit more complicated because it's heat and not electrons that are moving, but it's still related to that same idea. So I'm not going to talk about that in too much more detail. But they are good conductors. That's one of the key properties of metals. Again, fairly unique for metals. There's not many other types of substances that are good conductors. There's a couple that we'll talk about, but for the most part, other solid substances that we'll have are going to not be conductors like metals are. All right, so any questions on the properties of metals and how they're bonded to each other? All right, the bigger thing we're going to talk about today are the structures of crystalline metallic solids. And so before we get into that, we're going to give a little bit of background into how we determine the structures of these different materials. So how do we know how the atoms are arranged? How do we know that they're in this regular ordered pattern? How far apart they are from each other? All those things, how do we measure that? And so the experiment we use is called X-ray diffraction. So just as a little bit of an aside, what we're getting into now in this part of the course is going to be probably the closest thing we'll have in general chemistry to the branch of chemistry that's called inorganic chemistry, which is the branch of chemistry that I trained in. So it's pretty it's one I like the best, let's say it that way. So this is a topic called inorganic chemistry, which deals with the structures and properties of metals and compounds that involve metals. And one of the key techniques you use in that branch of chemistry is what's called X-ray diffraction. All right. And so what basically happens in X-ray diffraction is when an electromagnetic radiation, a wave of any type of electromagnetic radiation is going to be deflected by a regular pattern of points that are present. And so in a crystal, the regular patterns of points are the atoms that make up the crystal. And so when X-rays hit that pattern of points, they scatter off in different directions. So the key idea is that X-rays scatter off the atoms in a crystal. And so the math involved with X-ray diffraction, how you convert what's called the diffraction pattern to the structure is kind of complicated, but we're going to again just give the basics here. And so what happens when they scatter is that in some directions the X-rays are going to scatter and you're going to have constructive interference between the scattered X-rays. And so in that case the two waves will add up constructively and you'll get an enhancement in amplitude in that direction. But then in other directions, the scattered X-rays are going to be aligned in a destructive fashion, meaning that the peak of one wave is aligned with the crest of the other and vice versa. And so those are going to subtractively combine or out of phase combination, and that's going to be called destructive interference. And so the key idea here is that when you shine X-rays on a crystal, this is kind of a little picture of what happens. So you take an X-ray beam, you shine it on your crystal, which is shown here, and then you're going to get scattered X-rays in all directions, and the ones that scatter constructively are going to show up as little spots on your X-ray film. So in old school days, they literally used like camera film to do this. So they would measure the X-rays as they diffract off the crystal, and you get a pattern of spots on that film. And then you basically rotate the crystal around in different directions, measure that pattern in all different orientations, and you do a bunch of math to convert that pattern into the structure, the atoms that are present and how far apart they are and how they're arranged, all that stuff. So we're leaving out a lot of key details, but what we should be familiar with is that the spots that you see on the film, which now we use what's called a CCD to do this, so it's not a disposable photographic film anymore, but a sort of electronic device that measures this in a computerized fashion. But the spots on the plate represent the angles at which you get constructive interference. And what you'll notice if you look at these plates is you'll have, like, for example, lines of spots that kind of arrange themselves in a regular direction. And so the distance between those lines of spots is then related to the distance between planes of atoms in the crystal. So how close together the spots are on the plate is directly related to how close they are together in the structure. Actually, it's inversely related, I think, in some sense. But nonetheless, you can use those patterns of spots and how far apart they are from each other and all kinds of things to correlate this with the structure of the crystal. So to talk a little bit more about this constructive interference condition, the way that this happens is when you shine X-rays on the structure. So we're going to use lambda is going to be the wavelength of those X-rays. Most of this information is just background. We're not going to really test you guys too much on X-ray diffraction. It's a pretty advanced topic. But just to give you an idea of how this works. So what you do is your incident X-rays come in, and they're going to scatter off of different planes, different layers of atoms that are in the structure. And so what you can do is you can measure, again, the angle of the scattering here, theta. That's the angle they come in at and the angle they diffract at. And then you can correlate that to the distance between the two layers of atoms that the X-rays are scattering off of. Because in this case, the two X-rays are going to scatter constructively. You can see that the two waves, they're lined up, they're coming off at the same angle. So these would constructively interfere. And so what you have are a few different terms here that you can measure. So theta is the angle of incidence. And that's the angle of the X-ray beam relative to the surface of the crystal. So that's why we rotate the crystal around, so that we can get different angles as we measure different orientations. And then D here, which I'm showing here in this diagram there, D is the distance between planes of atoms. And that's what we're ultimately trying to come up with. And then what you have is the Bragg equation. So this was actually come up with by a father and son duo named Bragg, and they both won the Nobel Prize together. So I used to, play baseball with my dad. They were winning Nobel Prizes together. So everybody has different things they like to do with their parents. But anyway, what they came up with was this equation here. So n lambda, which is the wavelength, is equal to 2d sine theta. So that relates then the wavelength of the incident angle here, the wavelength, and then the distance between the two planes. And again, n here is an integer in this equation. So you have different integer values where this is going to be true. So it's n times lambda equals 2d sine theta. It's called the Bragg equation. So you basically measure, the wavelength of the X-rays you're using, and then you measure the angle at which you get these different constructive interferences, and that allows you to back out a distance between the planes. And so then knowing the distance between the planes of atoms, you piece that together in all three directions, and that gives you then the full lattice, the arrangement of all the atoms in all three directions. So really, X-ray diffraction is just repeated application of the Bragg equation here, which allows you to determine the distance between planes of atoms in a crystal, and that's how we determine the structure. So that's going to be just a little bit of background on how we do this. If you're wondering where does this information come from, it's not something that we just make up out of thin air. It is something that you can measure and experimentally validate. All right, so we're not going to go into more detail on that, but we are going to talk about, and what we're going to certainly have on the final exam for some of the questions are some questions about the structures of metallic and ionic solids. We'll start with metals today. So the ones we're going to talk about in most details are cubic structures. So again, what you have in this case is a unit cell that's defined as a cube, and then you're going to move that cube around in all three directions to generate the three-dimensional lattice of points that makes up that structure. And the atoms in the unit cell can be located in different parts of the cube, and depending on where they are in the cube, you're going to count that as in different ways. So one place you can put an atom is in the center of the cube, completely enclosed by that unit cell, and so we call that a body center position. So when we're defining these different types of structures we can have, so within the cubic cells we're going to have at least three different types to talk about, and what you're doing is you're putting atoms on different parts of those cubes to define that unit cell. And so one place you can put an atom is called body center. That's completely inside in the center of the cube. And so in that case, the atom is not shared, right? It's belonging entirely to that unit cell, all right? And so when it's not shared, it's going to count as a full atom. Because one thing we'll have to be able to do as part of defining these structures, just talk about how many atoms are there per unit cell. So if there's an atom in the bonding center, that counts as one atom for that unit cell because it's completely inside the cell and it's not shared by any of the neighboring cells. But then for the other places that we can put atoms, they're going to be shared by 2 or more unit cells. So if we put one on the center of one of the faces of the cube, so there's 6 faces in a cube, so each one of those can have up to 1 atom on the center of the face. That's called the face center position. And in that case, the atom would be shared by 2 unit cells, because when we stack the unit cells in all 3 directions, the 2 cells that are right next to each other with their neighboring faces are going to have an atom that's on each face of those cubes that's shared by 2 cells. All right, so when you stack these up in all directions, the face center positions are going to be shared by 2 unit cells. And so when we're counting that atom as how many atoms are in that single cell, it's going to count as 1/2 of an atom. All right, so each atom that's in a face center position counts as 1/2 for that specific unit cell, because it will be also shared in part of the unit cell that's next to it as you stack it side to side or top to bottom, right? The other place we can put atoms is in the edge position. We won't see this in metallic structures, but this will be something that we'll see in ionic structures in some cases. So if you have an atom on the edge of a unit cell, when you stack the cubes in all directions, you're going to have 4 cubes that share an edge. So you'll have basically 1 to the side, 1 to the front of it, and then 1 at the intersection of those 2. So you'll have, in this case, an edge position is shared by 4 unit cells. And so it counts as 1/4 of an atom for that specific cell when it's on an edge position. That's again because when you stack them in all directions, you'll have 4 cubes that share a single edge. If you have cubic blocks, it's maybe good to play with them at this point to understand this better. And then the other place where it's very common to have atoms, we'll see this in pretty much all the structures that we deal with, is at the corner of a cube. All right, so we can put atoms right in the corner of a cube. And in this case, it's going to be shared by 8 unit cells, because when we stack up unit cells, 8 cells are going to share a cube. 4 that are in the same layer as that cube, and the 4 on top of it as well, if we're talking about this position here. So you'll have the 4 that go in the same plane, and then the 4 that are on top of that will all share that same corner. And so when we count an atom that's in a cube, it counts as 1/8 of an atom for that specific unit cell. All right, so that's how we sort of count the atoms depending on where they are in the structure. And so those are the 4 major positions we're going to talk about in both metallic and ionic structures. So now let's get into the different types of metallic structures we have, where again, we're going to arrange atoms in different parts of these cubic unit cells, and then see how that changes some of the features of them. All right, so the first one is called simple cubic. I mean, the main thing you're going to have to know is sort of how to describe these structures and how to count the atoms that are in each unit cell. That's the important thing. We're going to talk about some other details as well that are sort of tangential, but the important thing, again, is going to be to talk about how to describe the structure. So in a simple cubic structure, we can think about these either in terms of how the atoms are arranged into the cubic unit cell. That's probably the more useful way to think about it. But it's also helpful to think about how would we generate these structures by taking layers of atoms and then stacking them on top of each other. So if you want to generate a simple cubic structure, you start with 1 layer of atoms, all of them sort of adjacent to each other. And then what you do, and this is the easiest one, is you just stack the next layers directly on top of the first. So these are what are called eclipsed layers. All the layers are eclipsed because they're all stacked directly on top of each other. Each adjacent sphere, which represents an atom, is directly on top of the one below it, and it has another one directly on top of it in the other direction. So they're just stacking the layers just like you would stack pancakes, just one on top of the other, all identical layers, all stacked with all the atoms perfectly lined up with each other. So that's how we generate the simple cubic structure in terms of layers of atoms that would be used to generate that. The more important thing to think about is how the atoms are arranged. So in a simple cubic structure, all you have is one atom in each corner of the cube, right? So that's what this is showing here. This one shows some space between the atoms, so it's easier to tell where they are. So in a simple cubic structure, it's one atom per cube. And then when we stack those cubes in all three directions, it would look like this. This is taking 8 of these cubes and stacking them together to generate this larger structure. But again, each unit cell is a cube. So that would be one unit cell that I'm highlighting in blue there. So you have those 8 cubic unit cells that are going to be stacked together in this picture here. And then this is what's called a space filling model. So this is showing that in reality you don't have these big gaps between the atoms. They're going to be arranged so that their atomic radii, the sort of outer boundary of where the electrons would be in them, are as close together as they can get. They're going to be packed as close together as possible. So in reality you don't have those big gaps, but you will have some small gaps in the structure, as you can see, but each atom is going to be touching along the 4 sides of each square face and along the edges as well. So you have the atoms as close together as possible when you build these structures. This is what's called a space filling model. So let's talk about some more geometric details about this structure. So what we're going to do is we're going to focus on one face of the cube here. All right, so we're going to focus on one face of the cube. So what you'll notice is that in one face you have an atom in each corner. That's what a simple cubic structure is. So you can sort of draw it in this way here. So this is a face of the cube, and you have part of an atom that's occupying each side of that. And so as you go along the side of a cube, what we're going to call the distance across the side is going to be abbreviated as A here. So in any cubic structure, the size of the unit cell, how long each side is on the cube, is going to be defined as A. And that, of course, is going to vary depending on what atom we have, what metal we have in the structure. And then in this structure here, the length of the side, as we go from one side, from one edge to the other, we go through one atomic radius for that corner, and then we go through a second atomic radius to get all the way to the other side. So there's a simple relationship here where the side length A is equal to 2 times the radius of the atom. So in a simple cubic structure, that's the relationship between the length of the side and the atomic radius. And so for all the different cubic structure types, we're going to have a relationship between the length of the side A and the radius of the atom R that's in that structure. So A is equal to 2R for a simple cubic structure. So what we can also do then is we can define what's called a packing efficiency. What percentage of the space is actually occupied by the atoms? Because as you can see, there is some gaps in the structure. Even though the atoms are packed as close together as they can be, there are still some gaps. We saw that up here as well. There's little holes in the structure. So we want to know what percentage of the volume of that cube is occupied by the atom. So what we're going to do is some calculations to get that. So first is the volume of the cube itself, which is A cubed. So the volume of any cube is just the side length cube. That's just from geometry. And in this case, A is equal to 2R, so we can rewrite that as 2R cubed, which is 8R cubed. And then the other thing we have to do to define packing efficiency is how many atoms or how many spheres are there in a single unit cell. And as we talked about, that's determined by where the atoms are located in that unit cell. So in a simple cubic structure, we have all 8 corners having one atom on them. That's all we have here. Atom, atom, atom up there. All 8 corners have an atom on it. So there's 8 corners, each with an atom on it. And as we said, the corner positions are shared by 8 unit cells, so each one will count as 1/8 of an atom for that individual unit cell. So we count each one of those as 1/8. And so in that, there's going to be 1 atom per unit cell in a simple cubic structure. And so then the volume of that atom is there's 1 atom, and the volume of a sphere is 4/3 times pi r cubed. So what we have is the volume of the atoms in the unit cell, or in this case just the single atom in that, is 4/3 pi r cubed. And then the packing efficiency is going to be defined again as the percentage of the volume that's taken up by the atoms, the spheres. So we're going to divide this by 8r cubed to figure out what the packing efficiency is. So for packing efficiency, we take the volume of the spheres in the unit cell, or the atoms as they are, and we divide that by the volume of the cube, and figure out what that percentage is, and we multiply it by 100 to get it to a percentage. So the volume of the spheres is 4/3 pi r cubed. The volume of the cube is 8r cubed, as we talked about above. We multiply that by 100, and simplifying it down, it comes out to pi over 6 times 100, which is 52.4%. So this means in any simple cubic structure, 52.4% of the volume is occupied by the atoms. The rest is empty space. So almost half of this is going to be empty space in this case. So that's another key thing we're going to classify about the different cubic unit cells are their packing efficiencies. This gives you some background on how to calculate it. We're not going to necessarily test you on all of this math and all this algebra, but the net result is important that we have 52.4% occupied volume in this structure. All right. Any questions on that, since that's the simplest of them? Yeah.
For the number of spheres being, so where do you get 8?
So there's 8 corners in a cube. So each cube has 1, 2, 3, 4, 5, 6, 7, 8 corners. Each of those corner positions counts as 1/8 of an atom because it's shared by 8 adjacent unit cells. So that'll be always the case when every corner is occupied. Okay?
Will this simple cubic structure always have a packing efficiency equal to 2.4%?
Yes. So no matter what, now the radius of the atoms is going to be different depending on what atom it is. So the size of the unit cell can be different because the length of the side is dependent on how big the atoms are that make it up. But the efficiency, the percentage of the volume that's occupied, will always be 52.4% for simple cubic. All right. So now we're going to move on to one that's slightly more complicated, which is body-centered cubic. So the way that we generate from layers is a little bit different. So what we're going to do in this case is we're going to place atoms in a layer, but we're going to leave a space in between each one. So in the previous structure, we saw that there was all the atoms were touching in each layer. Now we're going to arrange them with spaces in between. And then what we're going to do is we're going to stack the second layer over the first, over the gaps in the first. So it's the same type, it's really just one atom, I'm just drawing them in different colors so you can see the different layers more easily. So same atoms, same spacing between them, but now we're going to arrange them over the holes in the first layer. And so that's how we're going to stack the second layer. And then we're going to stack the third layer so that it eclipses the first. So it's just going to be an alternating pattern. So every other layer is going to be eclipsed, but there's going to be one in between them that occupies the gaps in those layers. All right, so there's going to be alternating layers where every other layer is going to be arranged in the spaces between the layers that are on top of it and below it. So what that generates then, if you pick out the cube from this, that's the smallest building block, is it's going to look like this. It's going to be called body-centered cubic. So what it's going to have is one atom in each corner. So there's 8 atoms in the corners, and then there's going to be one here in the body center. So it's kind of, in some sense, it's similar to simple cubic, but now we're forcing an atom in the center as well. So it's not just the 8 corners, but it's 8 corners plus one more stuffed in the middle. So that looks more complicated when you expand it out in all 3 directions, because the atoms are now closer together. It's a little bit hard to tell what's going on there. But then if you look at the space filling model, again, that's what you see. 8 corner positions, and then one stuffed in the middle of those 8 positions. That's what's called body-centered cubic. So that's how the atoms are arranged in this structure. So now let's go through a little bit of a geometric analysis for this. Now what we have to do for the body-centered cubic structure is we're going to work our way across a diagonal of the cube. So we're going to start down here and work our way all the way up to the opposite corner. So that's going to be this one here, So we're going to go through a diagonal of the cube from one corner to the opposite. and see what that looks like. So we're going to take out basically a two-dimensional slice in that direction. So geometrically, this one's a little bit more complicated. But again, what we're doing is going across a diagonal of the cube from one corner up to the exact opposite. So as we pass through that diagonal, what we go through is one atom that's in the corner, at the corner position. We go through the entire atom that's in the center, and we go through another atom that's in the opposite corner. So we're going to go through that here. So to find the relationship between the length of the cube, which is A, so A is again the length of each side of the cube, all identical. Here, this is going to be the cube diagonal here. And so in three-dimensional geometry, the diagonal squared is equal to the sum of the squares of the sides, which in this case are all the same A. So the diagonal is equal to A times the square root of 3. So then if we look at what's happening, the diagonal is equal to A radical 3. That's just geometry. And then as we go across the diagonal, we're going through the radius of the corner atom. We're going through 2 times the radius of the center atom, through the whole center atom, and then we're going through the radius of the atom that's in the opposite corner. So as we traverse across the diagonal, we pass through 4 atomic radii. 2 from the corners, the one in the center, which we pass through the whole thing. So A radical 3, which is the length of the diagonal, is equal to 4 times the radius, which means the relationship in this case is that the side length A is equal to 4r over the square root of 3. So the relationship between A and the atomic radius depends on the cubic structure that you have. So in the previous one, it was a simpler relationship, A equals 2r. Here it's more complicated because we have to go through a diagonal to see how those two relate to each other. Because on the face of a cube in this case, there's a little bit of a gap in between the atoms, as you can see, along each face. So we can't just go across the side of a cube anymore because the atoms are not touching along that side, so there's not a simple relationship. Again, a lot of these details you don't need to worry about too much, we're just sort of deriving things. The important one here, though, is to count how many spheres there are in the unit cell. That's something you absolutely have to be able to do. So in a body-centered cubic structure, we still have all 8 corners occupied. So those 8 atoms are going to count as 1/8 each for the corners. But we also have one atom that's in the direct center of the cube. So one atom in the center, and remember that each center position counts as a full atom, because that center position is not shared by any of the neighboring unit cells. That's completely inside of the unit cell. So for the center position, we count it as a full atom. And so in total, for this body-centered cubic structure, we have 2 atoms in the structure. 1 in net from the corners, 8 corners times 1/8 each, 1 in the center, total of 2. So now the volume of the spheres...
Absolute volume of X without 1 times 1. Like
Sorry?
the body center, like above, like that's 1 times 1, right?
Yes, 1 times 1. Because there's one atom in the center, and it counts as one whole atom because it's not shared by other unit cells.
Right.
So what we're doing for this math here is we're counting how many atoms are in those positions, 8 for the corners in this case, and then what percentage or what fraction of an atom do they count as for that unit cell. Each corner counts as 1/8. And then for the body center, there's one atom in the center, and it counts as a full atom because it's not shared by any other unit cell. So in net, there's 2 atoms in this body-centered cubic structure, so that means the volume of the spheres is going to be 2 times 4/3 pi r cubed. Which is 8/3 pi r cubed. And then to get the packing efficiency, we take, again, the volume of the spheres, which is 8/3 pi r cubed. We divide that by the volume of the cube itself in terms of the side length A. So the side length A is 4r over radical 3. So 4 over radical 3 r cubed. We multiply that by 100. So we can simplify this a little bit. R divides out, so it's just going to be 8/3 pi divided by 4 over radical 3 cubed. And numerically what that comes out to is 68.0%. All right, so if you multiply 8/3 pi and divide it by 4 over radical 3 cubed, you should get 68% after multiplying by 100. So in this structure here, 68% of the volume is occupied by the atom. So it's a more efficient packing. There's more of the space filled up, less empty space in a face-centered cubic structure. All right, and that's because, again, we're forcing an atom into the center of the cube. All right, so that's going to be the face-centered cubic, or sorry, body-centered cubic structure. I get those two mixed up sometimes. This is body-centered cubic. We're putting atom directly in the middle of the body of the cube. All right, and then the very last one we're going to cover for cubic structures is called face-centered cubic, and this is also going to be known as cubic close packed. So it turns out that body-centered cubic is not the most efficient way to pack spheres into a cube. This one here is. It's called cubic closest pack or cubic close packed. And this ends up being the most efficient way to do it. Now the layering in this case is going to be a little bit more complicated, but what you're going to start with is a close packed layer of spheres. And this is where we put the spheres as close together as they can be in a single layer. So we're not arranging them directly on top of each other. We're taking a line of atoms and then we're arranging the next one to fit in the gaps between the two. So we're making these as close together as possible. So we start with a close packed layer of spheres. So this represents the closest together these spheres can be if they're all arranged in a single layer. Imagine taking a bunch of marbles and trying to put them as close together as they can be. That's what it will look like. There's no extra gaps in there. And then you're going to take identical layers like this and stack them on top of each other in different ways. So the first layer, which I'll show in yellow here, I'll call layer A. The second layer, which is B, shown here in this picture with the open circles, is going to go over the little gaps in the first layer. So you'll notice that in these individual layers you have, I'll put it in red here so you can see it better, you have these little triangular gaps where three atoms all meet each other, right? And so the second layer is going to go so that the atoms in the second layer are directly over those little gaps in the first layer. So we're going to call that layer B. I'll do it all in blue. So that's going to be layer B, which is shown in blue-green there. And then the third layer is going to go above the gaps in the second layer. So these green ones, as they're shown here, are going to now go above the little triangular gaps in the second layer, and so we'll call that layer C. So when you stack all those on top of each other, you don't repeat the layers until you've gone through three separate layers. So you're going to have an A layer, a B layer, a C layer, and then you're going to start repeating the pattern after that. So it's called ABC or ABCA packing. Because now this other A layer here is now directly over the first A layer. So basically you don't eclipse two layers until you put two other ones in between them. So we call that ABC packing. You're going to stack them offset to each other 3 times, and then you'll start repeating the pattern after that. So it's A, B, C, and then the second A layer is directly over the first A layer, so that's where the pattern starts repeating. So it's ABC, or sometimes it's called ABCA packing. But again, it indicates that you have 3 layers stacked together, offset from each other, before you start repeating the pattern and doing that over again and over again. Now, it's not exactly obvious how these stacked layers can sort of end up being, into a cube. How do you take these layers of atoms and turn a cube into them? What you're really doing is going sort of in a sort of almost diagonal direction to generate the cubes. That's what this is showing here. So A will be in one corner, then the B layer, then the C layer, and then the A layer again. So that allows you to draw a cube, which ends up being what's called face-centered cubic. So translating from the layered structure to the cubic structure is hard to visualize, and so I don't necessarily expect you to be able to do that. But the way we want to think about this structure, again, is by focusing on the cubic unit cell. So we should know how it's generated from layers, but then how we're going to describe it is going to be in terms of this cubic unit cell. So in a face-centered cubic structure, you have 8 atoms in the corners, plus the 8th one that's kind of invisible from here. And then you also have the faces occupying with 1 atom each. So there's 6 faces in the cube, and each one of them has an atom in the center as well. So we don't have an atom directly in the center of the cube this time. In the body center, we have each face of the cube has an atom arranged on it. So that's what's called face-centered cubic. Each corner is occupied in all the structures, and this time it's the faces that are also occupied. All right. So in this case, if we can focus now again on one face of the cube here and talk about some of the geometric aspects of this. So if we look at one face of this cube here, again, the side length is defined as A, and then the diagonal, as we go through the diagonal of the face, we go through an atom that's in the corner that has a radius r. We go through an atom in the face center, which has a radius r, so in total 2r to go through that atom, and then another corner atom, which is a fourth r. So this time what we have is the length of a face diagonal, a squared plus a squared equals d squared if we're talking about a face diagonal. Before it was a body diagonal, or a cube diagonal. And so in this case, the diagonal is a square root of 2. And so this a square root of 2, which is the length of the diagonal across one corner of the face to the other, is equal to 4 times the radius, because we have to go through 4 atomic radii to traverse that diagonal. And that means the relationship in this case is that a is equal to 4r over square root of 2, which is equal to 2 square root of 2r in more simple terms. So this is the relationship, again, between a and radius. We don't necessarily expect you to memorize that, but that's how it comes from, and we're going to use that again to define the packing efficiency at the end. The most important part, as we said in this, is knowing how to count the atoms in the unicell. So in a face-centered cubic unicell, you have all 8 corners occupied, and each one counts as an eighth again, because they're shared by 8 unicells. And then we said that we also have all 6 faces occupied. So there's 6 faces in a cube, and they're all occupied. And each face is shared by 2 unicells. When you stack 2 cubes next to each other, they each share a face. So each atom that's in that face is going to be shared by 2 different cells. And so it's going to be counting as a half each. So in net, we have 4 atoms per unit cell in a face-centered cubic structure. 1 in net from the corners, each 8 corners occupy, and then 3 from the faces, all 6 faces counting as a half each. So 4 atoms in the unicell, which means that the volume of those atoms is 4 times 4/3 pi r cubed, where r is the atomic radius, or 16/3 pi r cubed. And then from there, we can again calculate packing efficiency. We take the volume of the spheres, which is 16/3 pi r cubed, and we divide that by the volume of the cube. So the side length of the cube is 2 radical 2r. And cubing that gives you the volume of the cube. So this is the volume of the spheres divided by the volume of the cube, multiplied by 100, and this comes out to 74%. And this ends up being the most efficient way that you can pack spheres into a cube. All right, so that's the highest you can get. So we saw it was about 52% for simple cubic, 68% for body-centered cubic, and now with face-centered cubic, we have a packing efficiency of 74%, meaning 74% of the volume of that cube is occupied by the atoms, only a little bit of empty space. All right, so that's the face-centered cubic structure. The last one we'll talk about, but again, not in as much detail, is called hexagonal close packed. So there's actually one other way that we can generate a close packed structure, but it's just going to be by arranging the layers a little bit differently. So in a hexagonal close packed structure, we start with the same types of layers, close packed layers, but this time we just go through ABA packing. So we're just going to stack 2 layers, and then the third layer is going to now eclipse the first layer instead of having alternating 3 layers. So in a hexagonal close packed structure, it's almost the same as cubic close packed, but it's going to be generated by just simple or AB, or what we sometimes call ABA packing, where we're just alternating 2 layers and then repeating the pattern after that. All right, so it's still the same close packed layers, but just stacked a little bit differently. And so if we look at the number of atoms in a unit cell for hexagonal structure, it's a little bit different here. So for a hexagonal unit cell, it's not really a cube anymore. The angles are no longer 90 degrees, basically. So that's what it looks like. The number of atoms in this case, you have 12 atoms that are shared by 12 unit cells. So there's they're shared by 6 unit cells. And then you have 3 in the center, and then you have 2 that are on the faces. Again, we're not going to really test you guys on these ones, but the important thing to know for hexagonal close packing is that the packing efficiency is exactly the same. So hexagonal close packing is a lot harder to visualize because it's no longer a nice cube, but what you have again is sort of a hexagon of atoms. That's why we call it hexagonal, where you have those 12 or those 6 plus the 6 below it are going to be shared by 12 unit cells. You have 3 in the direct middle, and then these 2 that are in the center of a face that's shared. So it's harder to visualize the structure, so we're not going to go through it in more detail. But the only difference again is just how we generate it by stacking the layers differently. And the important thing to know is that the packing efficiency for hexagonal and cubic close packed are identical. So there are 2 alternative structure types that have identical packing efficiency. So it's very complicated to know why does some metals adopt one and not the other, but this is the other way to get that close packing, that most efficient arrangement of spheres into a 3-dimensional structure. Okay? But that's going to be, again, just a structure we're going to talk about only in a little bit of detail. So we're not going to do anything beyond this, so don't worry about that one too much. The next thing we're going to define for each structure is what's called the coordination number. And so this is going to be defined as the number of nearest neighbors for any atom in the structure. In other words, this is going to be the number of other atoms an atom is touching in that crystal structure. All right. So in a simple cubic structure, let's talk about the coordination number in this structure. It's probably easiest to think about it in terms of the layers that we use to make it up. So remember, in simple cubic, we're going to take a layer that looks like this, a totally eclipsed layer, and we're just going to stack them on top of each other directly. So if we focus on one atom in that layer, I'm going to put an X through that one. Let's think of how many other atoms that atom is touching. So in the same layer as that one, there's going to be 4 that are touching that atom directly. So those 4 atoms are touching. And then remember, we're stacking the layers in all directions. So you're going to also have another one on top of it in the layer above, and you're going to have another one below it in the layer below. So you're going to have those 4 atoms in the same layer plus one above and below. And so that means an atom in a simple cubic structure has 6 nearest neighbors, 6 atoms that are touching it. 4 in the same layer, 1 in the layer above, 1 in the layer below. But the important thing to know is that the coordination number then, abbreviated as Cn, is going to be 6 for a simple cubic structure. Okay? Another way to look at this is to look at this atom here in the center. This atom there is going to be bordering 1, 2, 3, 4, 5, 6 others. 6 is coordination number in this case. So in a simple cubic structure, each atom is bordered by 6 others. That's the coordination number. If we go to body-centered cubic, this one's actually probably the simplest to determine the coordination number for. So in a body-centered cubic, think about the atom that's in the center here, and how many atoms is it closest to? Well, it's going to be touching all the atoms that are at the corners. So the atom in the center is sort of completely surrounded by the 8 corner atoms, and so there's going to be 1, 2, 3, 4, 5, 6, 7, 8. So this coordination number is going to be 8 for the body-centered cubic. And then finally, for cubic close packing, whether it's hexagonal or cubic, the coordination number again is a little bit more complicated to determine, so we're going to go through it in a little bit. So let's focus on this atom here in this layer with open circles. So when you look at the closest packing arrangement, each atom in the same layer is going to be surrounded by 6 others that are completely touching it. And that's, again, the closest you can put them together. So 1, 2, 3, 4, 5, 6. But then if we look at that same atom and think about the layers that are above it, we have right above it 3 atoms that are touching it. So how did I write that? Oh, and then also below it. So below this we have those yellow spheres that are going to be 7, 8, and 9 that are touching it. And then above it we're going to have 3 more that are also touching it, which would be 10, 11, 12. So what you have in the cubic close packing structure, where again thinking about the layers is probably the simplest way to rationalize this. 6 atoms in the same layer that are touching it, 3 that are above it in the layer above, and 3 that are below in the layer below. And so the ones that are marked in yellow, that are shown in yellow, are going to be the layers that are below that one. The ones that are shown in green here are the 3 that are above it. But in total, that means the coordination number for this is going to be 12. All right, so for the 3 different structure types, you have 3 different coordination numbers, which then correlate with the packing efficiencies. The one that has the least efficient packing has the smallest coordination number, body center and cubic in the middle with 8, and the most efficient packing also has the highest coordination number. The most number of atoms that are touching a single atom in that structure, which is in part why it has that higher packing efficiency. All right, so that's another definition. So what we'll do next time is we'll summarize that before moving on to other types of solid structures. All right, and that should take us to the end of chapter 9.